Hello and welcome to Electronics Learning YouTube channel. This is second part of chapter 2. Our next topic is Zener Diodes. The Zener diode or breakdown diode are basically the same as the standard PN junction diode, but they are specially designed to have a low and specified reverse breakdown voltage which takes advantage of any reverse voltage applied to it. The Zener diode behaves just like a normal general-purpose diode consisting of a silicon PN junction, and when biased in the forward direction, that is anode positive with respect to its cathode, it behaves just like a normal signal diode passing the rated current. However, unlike a conventional diode that blocks any flow of current through itself when reverse biased, that is, the cathode becomes more positive than the anode. As soon as the reverse voltage reaches a predetermined value, the Zener diode begins to conduct in the reverse direction. This is because when the reverse voltage applied across the Zener diode exceeds the rated voltage of the device, a process called avalanche breakdown occurs in the semiconductor depletion layer and a current starts to flow through the diode to limit this increase in voltage. The voltage point at which the voltage across the Zener diode becomes stable is called the Zener voltage, Vz, and for Zener diodes this voltage can range from less than 1 volt to a few hundred volts. The fact that the voltage across the diode in the breakdown region is almost constant turns out to be an important characteristic of the Zener diode, as it can be used in the simplest types of voltage regulator applications. The function of a regulator is to provide a constant output voltage to a load connected in parallel with it in spite of the ripples in the supply voltage or the variation in the load current, and the Zener diode will continue to regulate the voltage until the diode's current falls below the minimum value in the reverse breakdown region. Zener diodes can be used to produce a stabilized voltage output with low ripple under varying load current conditions. By passing a small current through the diode from a voltage source, via a suitable current limiting resistor, RS, the Zener diode will conduct sufficient current to maintain a voltage drop. Resistor RS is selected so to limit the maximum current flowing in the circuit. Note that with no load connected to the circuit, the load current will be zero, and all the circuit current passes through the Zener diode, which in turn dissipates its maximum power. One small problem with Zener diode stabilizer circuits is that the diode can sometimes generate electrical noise on top of the DC supply as it tries to stabilize the voltage. Normally this is not a problem for most applications, but the addition of a large value decoupling capacitor across the Zener's output may be required to give additional smoothing. As well as producing a single stabilized voltage output, Zener diodes can also be connected together in series along with normal silicon signal diodes to produce a variety of different reference voltage output values as shown. A typical Zener diode for general electronic circuits is the 500 mW BZX55 series or the larger 1.3 watts BZX85 series, where the Zener voltage is given as, for example, C7V5 for a 7.5 volts diode, giving a diode reference number of BZX55C7V5. What if the input signal was not steady-state DC but an alternating AC waveform? How would the Zener diode react to a constantly changing signal? Diode clipping and clamping circuits are circuits that are used to shape or modify an input AC waveform, or any sinusoid, producing a differently shaped output waveform depending on the circuit arrangement. Diode clipper circuits are also called limiters because they limit or clip off the positive or negative part of an input AC signal. As Zener clipper circuits limit or cut off part of the waveform across them, they are mainly used for circuit protection or in waveform shaping circuits. For example, if we wanted to clip an output waveform at plus 7.5 volts, we would use a 7.5 volts Zener diode. If the output waveform tries to exceed the 7.5 volts limit, the Zener diode will clip off the excess voltage from the input, producing a waveform with a flat top, still keeping the output constant at plus 7.5 volts. Note that in the forward bias condition, a Zener diode is still a diode, and when the AC waveform output goes negative below minus 0.7 volts, the Zener diode turns on like any normal silicon diode would and clips the output at minus 0.7 volts as shown. The back-to-back connected Zener diodes can be used as an AC regulator, producing what is jokingly called a poor man's square wave generator. Using this arrangement, we can clip the waveform between a positive value of plus 8.2 volts and a negative value of minus 8.2 volts for a 7.5 volts Zener diode. So for example, if we wanted to clip an output waveform between two different minimum and maximum values of, say, plus 8 volts and minus 6 volts, we would simply use two differently rated Zener diodes. Note that the output will actually clip the AC waveform between plus 8.7 volts and minus 6.7 volts due to the addition of the forward biasing diode voltage. This type of clipper configuration is fairly common for protecting an electronic circuit from overvoltage. Our next topic is light-emitting diodes. They are the most visible type of diode that emit a fairly narrow bandwidth of either visible light at different colored wavelengths, invisible infrared light for remote controls, or laser-type light when a forward current is passed through them. Light-emitting diodes are made from a very thin layer of fairly heavily doped semiconductor material, and depending on the semiconductor material used and the amount of doping, when forward biased, an LED will emit a colored light at a particular spectral wavelength. When the diode is forward biased, electrons from the semiconductor's conduction band recombine with holes from the valence band, releasing sufficient energy to produce photons which emit a monochromatic of light. Because of this thin layer, a reasonable number of these photons can leave the junction and radiate away, producing a colored light output. When operated in a forward-biased direction, light-emitting diodes are semiconductor devices that convert electrical energy into light energy. The p-n junction of an light-emitting diode is surrounded by a transparent, hard plastic epoxy resin hemispherical-shaped shell or body which protects the light-emitting diode from both vibration and shock. Surprisingly, an LED junction does not actually emit that much light, so the epoxy resin body is constructed in such a way that the photons of light emitted by the junction are reflected away from the surrounding substrate base to which the diode is attached and are focused upwards through the dome top of the LED, which itself acts like a lens, concentrating the amount of light. This is why the emitted light appears to be brightest at the top of the LED. Also, nearly all modern light-emitting diodes have their cathode negative terminal identified by either a notch or flat spot on the body, or by the cathode lead being shorter than the other, as the anode positive lead is longer than the cathode. Light-emitting diodes are made from exotic semiconductor compounds such as gallium arsenide, gallium phosphide, gallium arsenide phosphide, silicon carbide, or gallium indium nitride, all mixed together at different ratios to produce a distinct wavelength of color. The exact choice of the semiconductor material used will determine the overall wavelength of the photon light emissions and therefore the resulting color of the light emitted. Thus, the actual color of a light-emitting diode is determined by the wavelength of the light emitted, which in turn is determined by the actual semiconductor compound used in forming the p-n junction during manufacture. Recently developed blue and white colored LEDs are also available, but these tend to be much more expensive than the normal standard colors due to the production costs of mixing together two or more complementary colors at an exact ratio within the semiconductor compound, and also by injecting nitrogen atoms into the crystal structure during the doping process. From the table above, we can see that the main p-type dopant used in the manufacture of light-emitting diodes is gallium, and that the main n-type dopant used is arsenic, giving the resulting compound of gallium arsenide crystalline structure. Like conventional p-n junction diodes, light-emitting diodes are current-dependent devices with its forward voltage drop Vf, depending on the semiconductor compound and on the forward-biased LED current. Most common LEDs require a forward operating voltage of between approximately 1.2 to 3.6 volts with a forward current rating of about 10 to 30 mA, with 12 to 20 mA being the most common range. As with series resistors, LEDs connected in series all have the same forward current, IF, flowing through them as just one. As all the LEDs connected in series pass the same current, it is generally best if they are all of the same color or type. If we assume that the three LEDs are to be illuminated from the 5-volt logic device or supply with a forward current of about 10 mA, then the voltage drop across the resistor, Rs and its resistance value will be calculated as. Now that we know what an LED is, we need some way of controlling it by switching it on. The output stages of both TTL and CMOS logic gates can both source and sink useful amounts of current, therefore can be used to drive an LED. Normal integrated circuits have an output drive current of up to 50 mA in the sink mode configuration, but have an internally limited output current of about 30 mA in the source mode configuration. IC driver circuit is shown. If more than one LED requires driving at the same time, such as in large LED arrays, or the load current is too high for the integrated circuit, or we may just want to use discrete components instead of ICs, then an alternative way of driving the LEDs using either bipolar NPN or PNP transistors as switches. Transistor driver circuit is shown. The brightness of a light-emitting diode cannot be controlled by simply varying the current flowing through it. LEDs are designed to produce a set amount of light operating at a specific forward current ranging from about 10 to 20 mA. A bicolor light-emitting diode has two LED chips connected together in inverse parallel, one forwards, one backwards, combined in one single package. The most popular type of tricolor light-emitting diode comprises of a single red and a green LED combined in one package with their cathode terminals connected together, producing a three-terminal device. These tricolored LEDs can also generate additional shades of their primary colors, the third color, such as orange or yellow, by turning on the two LEDs in different ratios of forward current as shown in the table, thereby generating four different colors from just two diode junctions. A standard 7-segment LED display generally has 8 input connections, one for each LED segment and one that acts as a common terminal or connection for all the internal segments. In the common cathode display, all the cathode connections of the LEDs are joined together and the individual segments are illuminated by application of a high, logic 1 signal. In the common anode display, all the anode connections of the LEDs are joined together and the individual segments are illuminated by connecting the terminals to a low, logic 0 signal. Finally, another useful application of light-emitting diodes is optocoupling. An optocoupler, or optoisolator as it is also called, is a single electronic device that consists of a light-emitting diode combined with either a photodiode, phototransistor or phototriac to provide an optical signal path between an input connection and an output connection while maintaining electrical isolation between two circuits. An optoisolator consists of a light-proof plastic body that has a typical breakdown voltages between the input, photodiode, and the output, phototransistor, circuit of up to 5000 volts. This electrical isolation is especially useful where the signal from a low-voltage circuit such as a battery-powered circuit, computer or microcontroller, is required to operate or control another external circuit operating at a potentially dangerous mains voltage. Optoisolators are digital or switching devices, so they transfer either on/off control signals or digital data. Analog signals can be transferred by means of frequency or pulse width modulation. Our next topic is solar bypass diodes. Bypass diodes, which in electronics we know as freewheeling diodes, are wired in parallel with individual solar cells or panels, to provide a current path around them in the event that a cell or panel becomes faulty or open-circuited. This use of bypass diodes allows a series, called a string, of connected cells or panels to continue supplying power at a reduced voltage rather than no power at all. Bypass diodes are connected in reverse bias between a solar cells, or panel, positive and negative output terminals and has no effect on its output. A solar panel is constructed using individual solar cells, and solar cells are made from layers of silicon semiconductor materials. One layer of silicon is treated with a substance to create an excess of electrons. This becomes the negative or N-type layer. The other layer is treated to create a deficiency of electrons, and becomes the positive or P-type layer similar to transistors and diodes. In fact, photovoltaic solar cells, or PVs as they are more commonly called, are no more than big, flat photosensitive diodes. Photovoltaic solar cells convert the photon light around the p-n junction directly into electricity without any moving or mechanical parts. PV cells produce energy from sunlight, not from heat. In fact, they are most efficient when they are cold. When exposed to sunlight, or other intense light source, the voltage produced by a single solar cell is about 0.58 volts DC, with the current flow, amps, being proportional to the light energy, photons. In most photovoltaic cells, the voltage is nearly constant, and the current is proportional to the size of the cell and the intensity of the light. The silicon wafer of the photovoltaic solar cell that faces the sunlight consists of the electrical contacts and is coated with an anti-reflective coating that helps absorb the sunlight more efficiently. When sunlight shines on a photovoltaic cell, photons of light strike the surface of the semiconductor material and liberate electrons from their atomic bonds. During manufacture, certain doping chemicals are added to the semiconductor's composition to help to establish a path for the freed electrons. These paths creates a flow of electrons forming an electrical current which starts to flow over the surface of the photovoltaic solar cell. Most photovoltaic solar cells produce an load open circuit voltage of about 0.5 to 0.6 volts when there is no external circuit connected. This output voltage depends very much on the load current, I demands of the PV cell. For example, on very cloudy or dull day the current demand would be low and so the cell could provide the full output voltage, but at a reduced output current. But as the current demand of the load increases, a brighter light, solar radiation, is needed at the junction to maintain a full output voltage. However, there is a physical limit to the maximum current that a single photovoltaic solar cell can provide no matter how intense or bright the sun's radiation is. This is called the maximum deliverable current and is symbolized as Imax. The Imax value of a single photovoltaic solar cell depends upon the size or surface area of the cell, especially the p-n junction, the amount of direct sunlight hitting the cell, its efficiency of converting this solar power into a current and of course the type of semiconductor material that the cell is manufactured from, either silicon, gallium arsenide, cadmium sulfide or cadmium telluride, etc. So when selecting blocking diodes or bypass diodes to connect to solar cells or panels, this maximum current value, Imax, needs to be taken into account. Diodes can be used to block the flow of electric current from other parts of an electrical solar circuit. When used with a photovoltaic solar panel, these types of silicon diodes are generally referred to as blocking diodes. Bypass diodes are used in parallel with either a single or a number of photovoltaic solar cells to prevent the currents flowing from good, well exposed to sunlight solar cells overheating and burning out weaker or partially shaded solar cells by providing a current path around the bad cell. Blocking diodes are used differently than bypass diodes. Bypass diodes in solar panels are connected in parallel with the photovoltaic cell or panel to shunt the current around it, whereas blocking diodes are connected in series with the PV panels to prevent current flowing back into them. These blocking diodes, also called a series diode or isolation diode, ensure that the electrical current only flows in one direction out of the series array to the external load, controller or batteries. The reason for this is to prevent the current generated by the other parallel connected PV panels in the same array flowing back through a weaker, shaded, network and also to prevent the fully charged batteries from discharging or draining back through the array at night. So when multiple solar panels are connected in parallel, blocking diodes should be used in each parallel connected branch. Two types of diodes are available as bypass diodes in solar panels and arrays, the p-n junction silicon diode and the Schottky barrier diode. Both are available with a wide range of current ratings. The Schottky barrier diode has a much lower forward voltage drop of about 0.4 volts as opposed to the p-n diode's 0.7 volt drop for a silicon device. And our last topic is diode clipping circuits. The diode clipper, also known as a diode limiter, is a wave-shaping circuit that takes an input waveform and clips or cuts off its top half, bottom half or both halves together. To produce diode clipping circuits for voltage waveforms at different levels, a bias voltage, V bias, is added in series with the diode as shown. The voltage across the series combination must be greater than V bias plus 0.7 volts before the diode becomes sufficiently forward biased to conduct. For example, if the V bias level is set at 4.0 volts, then the sinusoidal voltage at the diode's anode terminal must be greater than 4.0 plus 0.7 equals 4.7 volts for it to become forward biased. Any anode voltage levels above this bias point are clipped off. The advantage of biased diode clipping circuits is that it prevents the output signal from exceeding preset voltage limits for both half cycles of the input waveform, which could be an input from a noisy sensor or the positive and negative supply rails of a power supply. The use of a bias voltage means that the amount of the voltage waveform that is clipped off can be accurately controlled. But one of the main disadvantages of using voltage-biased diode clipping circuits is that they need an additional EMF battery source, which may or may not be a problem. One easy way of creating biased diode clipping circuits without the need for an additional EMF supply is to use Zener Diodes. Here ends our chapter 2. Thank you for watching. Please subscribe our channel for more electronic theories. Goodbye.